Although we're going to be focusing on fallacies in Unit 4, today I want to start off by talking about something that might or might not be a fallacy. But in any case, it exposes a linguistic phenomenon that's called vagueness and that does create fallacies. Okay, so what is the thing I'm going to talk about today? Well, it's a phenomenon I call the argument from the heap, or sometimes called the Sorites argument, after the Greek word soros, which means heap. What's the argument from the heap? Well, let me give you an example. Consider the following argument. This is an example of the argument from the heap. Premise 1, a person who owns only 1 penny is poor. Premise 2, a person who owns only 1 penny more than a poor person is also poor. Conclusion, therefore, a person who owns a gazillion pennies is poor. Now, why should we believe that those premises support that conclusion? Well, think of it this way. If premise 1 is true, then a person who owns only 1 penny is poor. But if premise 2 is true, then it's going to follow that a person who owns 2 pennies is also poor, right? Because they own only 1 penny more than a poor person. And anyway, that's obviously right. A person who owns only 2 pennies is clearly poor. And then it's going to follow by premise 2 that a person who owns 3 pennies is also poor, right? Because they only own just 1 penny more than a poor person. So they're also going to be poor. And by premise 2, it's also going to follow that a person who owns 4 pennies is poor. Now, I hope you can see the pattern here. You can see where this is going. We can keep on applying premise 2 to our results, and we'll get that a person who owns 4 pennies is poor, a person who owns 5 pennies is poor, a person who owns 6 pennies is poor, and we can go on and on and on to 1,000,000 pennies, 1,000,000,000 pennies, 1,000,000,000,000 pennies, 1,000,000,000,000 pennies, and even a gazillion pennies. Now, there's a name for that kind of reasoning, which is common in mathematics. It's called the principle of mathematical induction. The principle of mathematical induction says that arguments of the following form are valid. Where premise 1 says the number 0 belongs to some category F, in our example, the category of numbers such that anyone who owns that number of pennies is poor. If X belongs to F, then X plus 1 belongs to F, that's premise 2. So in other words, that's saying that if a particular number of pennies is such that anyone who owns just that number of pennies is poor, then adding 1 to that particular number of pennies will also leave the person poor. And the conclusion is of the form all natural numbers belong to F. In other words, no matter how many pennies you own, you're still going to be poor. Right? All natural numbers belong to the category of numbers such that a person who owns that number of pennies is poor. That's the principle of mathematical induction, stated quite generally. Now, that principle, I'm quite confident, is correct. Right? Arguments of that form are valid. If arguments of that form weren't valid, then a whole lot of mathematics that mathematicians accept today would be false. And I don't believe it is. So, the principle of mathematical induction, I'm prepared to say, is correct. But then, what's going on in this argument? Right? If the principle of induction is correct, then it looks like the argument is valid. So if the argument is valid, that means there's no possible way for the premises to be true while the conclusion is false. So, is premise 1 true? Is it true that a person who owns only 1 penny is poor? Seems quite obviously yes. Premise 1 is true. A person who owns only 1 penny has got to be poor. And there's nowhere in the world where 1 penny makes you rich. What about premise 2? If you own just 1 penny more than a poor person, could you avoid being poor by owning just 1 penny more than a poor person? I don't see how you can. Right? 1 penny can't make the difference between being poor and not being poor. So it looks like premise 2 is true. But if the argument is valid and both of the premises are true, then that means the argument is sound. And remember, in a sound argument, the conclusion has to be true. So let's consider the conclusion. A person who owns a gazillion pennies is poor. Is that true? Well, no, it's not true. I wish I owned a gazillion pennies. Owning a gazillion pennies does not leave you poor. Someone who owns a gazillion pennies is very, very wealthy. So the conclusion seems to be obviously false. So what's going on here? Well, in logic, this is what we call a paradox. A paradox is an argument in which all of the premises of the argument seem to be obviously true, as in our argument from the heap. The argument seems to be obviously valid, again, as in our argument from the heap, but the conclusion seems to be obviously false, again, as in our argument from the heap. So our argument from the heap is one example of a paradox. There are many other examples. Now, some paradoxes are fallacies because despite appearances, even though they appear to be valid, they're really not. Really, they're arguments in which the premises don't support the conclusion, despite appearances. So some paradoxes are fallacies. But the question is this particular paradox a fallacy? Is the argument from the heap a fallacy? Or is it just a paradox? And if it is a paradox, what's the solution? Should we say that a person could avoid being poor even though they own only 1 penny? Should we say that you could avoid being poor by owning just 1 penny more than a poor person? Or should we deny the principle of mathematical induction? Or should we say that even if you own a gazillion pennies, you're still poor? How should we solve this paradox? I'll leave that for you to think about.